Whenever you are solving an LP, you are also solving another LP, which is its twin. We call this a dual of the LP. Here, we are going to discuss how to get the dual of an LP and their relationships. First, we define our terms. The original or the given LP is called the primal LP, and the dual is called the dual LP. If the primal LP is a maximization problem, then its dual is a minimization problem and vice versa. This is true for all LPs. Consider the following primal LP, maximization in matrix form. Max z is equal to cx such that ax is less than or equal to b, while x is greater than or equal to 0. Then, its dual can be written as minimization in matrix form, min w is equal to yb, such that ya is greater than or equal to c, and y is greater than or equal to 0. Since they are in matrix form, the order is important. From this, we can say that the A matrix is only transposed in the dual, and the positions of the B and C matrices are just interchanged. In summary, you can look up on this table for the construction of the dual LP from the primal LP. A variable is said to be normal if it is required to be non-negative. On the other hand, a normal constraint for a max problem gives an upper bound to the LP, and for a minimum problem, it gives the LP a lower bound. Therefore, a normal maximization-minimization LP can be defined as an LP with normal constraints and variables, as seen from the table. This table is helpful in constructing the dual of LPs. Also, from the table, we can see the relationships between the primal constraints, or variables, and the dual constraints, or variables. The ith constraint of one LP corresponds to the ith variable of the other, and vice versa. For example, we are given the following normal maximization LP. Max z is equal to 60x sub 1 plus 30x sub 2 plus 20x sub 3, such that 8x sub 1 plus 6x sub 2 plus x sub 3 is less than or equal to 48. 4x sub 1 plus 2x sub 2 plus 1.5x sub 3 is less than or equal to 20. 2x sub 1 plus 1.5x sub 2 plus 0.5x sub 3 is less than or equal to 8, while x sub 1, x sub 2, and x sub 3 are all greater than or equal to 0. Using our table, we can construct the dual of this LP. Min w is equal to 48 y sub 1 plus 20 y sub 2 plus 8 y sub 3, such that 8 y sub 1 plus 4 y sub 2 plus 2 y sub 3 is greater than or equal to 60. 6 y sub 1 plus 2 y sub 2 plus 1.5 y sub 3 is greater than or equal to 30. Y sub 1 plus 1.5 y sub 2 plus 0.5 y sub 3 is greater than or equal to 20. Y sub 1, y sub 2, and y sub 3 are all greater than or equal to 0. You can see that the columns and the rows were just interchanged, since the dual coefficients matrix is just the transpose of the primal coefficients matrix. Unfortunately, not all LPs are normal LPs. Take the following as an example. Max z is equal to 2x sub 1 plus x sub 2, such that x sub 1 plus x sub 2 is equal to 2, 2x sub 1 minus x sub 2 is greater than or equal to 3, x sub 1 minus x sub 2 is less than or equal to 1, x sub 1 is greater than or equal to 0, and x sub 2 is URS. It is not a normal max problem because it has an equality constraint. A is greater than or equal to constraint, and an unrestricted unsigned variable. You can opt to convert this non-normal LP into a normal LP by following these steps. Number 1, equality constraints should be replaced by two inequality constraints. A is greater than or equal to constraint, and A is less than or equal to constraint. X sub 1 plus x sub 2 is equal to 2. X sub 1 plus x sub 2 is less than or equal to 2, and x sub 1 plus x sub 2 is greater than or equal to 2. Number 2, all non-normal constraints, including constraints from number 1, should be multiplied by -1 to convert it to a normal constraint. 2x sub 1 minus x sub 2 is greater than or equal to 3, transforms into negative 2x sub 1 plus x sub 2 is less than or equal to negative 3. X sub 1 plus x sub 2 is greater than or equal to 2 transforms into negative x sub 1 minus x sub 2 is less than or equal to negative 2. Number 3, as you learned from LP formulation, unrestricted variables are transformed into normal variables by doing the following. X sub 2 is equal to x sub 2 plus minus x sub 2 minus 1. You can now change all x sub 2 variables into x sub 2 plus minus x sub 2 minus 1. We now arrive to the following normal max LP. Max z is equal to 2x sub 1 plus x sub 2 plus minus x sub 2 minus 1, such that x sub 1 plus x sub 2 plus minus x sub 2 minus 1 is less than or equal to 2. Negative x sub 1 minus x sub 2 plus x sub 2 minus 1 is less than or equal to negative 2. Negative 2x sub 1 plus x sub 2 plus minus x sub 2 minus 1 is less than or equal to negative 3. X sub 1 minus x sub 2 plus x sub 2 minus 1 is less than or equal to 1. X sub 1, x sub 2 plus and x sub 2 minus 1 are all greater than or equal to 0. From this, we can now get the dual of the max LP by transposing the matrix. Min W is equal to 2y sub 1 minus 2y sub 2 minus 3y sub 3 plus y sub 4, such that y sub 1 minus y sub 2 minus 2y sub 3 plus y sub 4 is greater than or equal to 2. Y sub 1 minus y sub 2 plus y sub 3 minus y sub 4 is greater than or equal to 1. Negative y sub 1 plus y sub 2 minus y sub 3 plus y sub 4 is greater than or equal to negative 1. Y sub 1, y sub 2, y sub 3, and y sub 4 are all greater than or equal to 0. You can do this long method of transforming it first into a normal LP, or just use our table for the transformations. Based on the table, we can arrive at the following dual of the original non-normal maximization LP. Min W is equal to 2y sub 1 plus 3y sub 2 plus y sub 3, such that y sub 1 plus 2y sub 2 plus y sub 3 is greater than or equal to 2, y sub 1 minus y sub 2 minus y sub 3 is equal to 1, y sub 1 is unrestricted, while y sub 2 is less than or equal to 0, and y sub 3 is greater than or equal to 0. From the table, we easily got the dual of the LP. X sub 2, unrestricted, causes the second dual constraint to be an equality constraint. Also, the first primal constraint being an equality constraint makes y sub 1 unrestricted. The second primal constraint, being a greater than or equal to constraint, makes y sub 2 less than or equal to 0. Weak duality. We now go to the concept of weak duality. Weak duality states that for any primal feasible point x, Cx is less than or equal to yb, and z is less than or equal to w. This means that for any iteration of the primal, its objective function value must always be less than or equal to the objective function of the dual. Remember that weak duality only applies to any primal feasible point. Fundamental theorem of duality. The fundamental theorem of duality states that for a given LP, only one of the following is true. Number 1, both the primal and the dual have optimal solutions. Number 2, one has an unbounded solution while the other is infeasible. And number 3, both are infeasible. Just a note for number 2, we know that an LP can have an unbounded feasible region but still have an optimal value, as discussed in the other video. In this case, since it has an optimal solution, the LP falls in statement number 1.